Hello, and welcome to the Palette Explainer. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, this journey is designed just for you. There's nothing demanding your attention right now, no tasks to complete, no problems to solve. Just you, this moment, and the vast, beautiful universe waiting to unfold in your mind. Tonight, we're going to explore the cosmos together, not with urgency or excitement, but with calm wonder. We'll move gently through facts about space, time, stars, and the quiet mechanisms that govern everything. Some of these ideas might surprise you. Others might feel like old friends, familiar and comforting. And if somewhere along the way you find yourself drifting into sleep, that's perfectly fine. That's exactly what this is for. So settle in, get comfortable, let your breathing slow, and let's begin this gentle exploration of everything. The fabric of space and time. Space is not a stage where events happen. It's more like a living fabric, flexible and responsive. According to Einstein's theory of general relativity, massive objects don't just sit in space, they bend it, curve it, shape it around themselves, like a heavy ball resting on a stretched sheet. This curvature is what we experience as gravity. When you drop something, it's not being pulled down by a force in the traditional sense. It's following the natural contour of curved space-time, moving along the path that bent space creates. This means that gravity isn't really a force at all. It's geometry. It's the shape of the universe responding to mass. Time works the same way. It's not absolute or universal. It flows at different rates depending on where you are and how fast you're moving. Near massive objects, time slows down. High in orbit, away from Earth's gravity, time moves slightly faster. This isn't theory anymore. It's measurable, practical reality. GPS satellites have to account for this time dilation, or they'd give you the wrong directions. So as you lie here now, time is flowing through you at its own particular rate, shaped by the mass of the Earth beneath you, by your position in space, by the subtle pull of everything around you. Time is personal, it's local, and it's flowing just right for this moment. Einstein spent years working on these ideas, refining them, testing them against observations. His equations described a universe that was dynamic, not static. Space could stretch, time could bend, and mass could tell space-time how to curve, while curved space-time told mass how to move. It was a conversation, a dance between matter and the fabric of reality itself. And the beautiful thing is that this isn't just abstract mathematics. We can measure it. We can see it. When light from distant stars passes near the sun during a solar eclipse, it bends, following the curve of space-time around the sun's mass. This was one of the first confirmations of Einstein's theory, observed during the solar eclipse of 1919. The universe was telling us that space itself could be shaped.
Galaxies like slow rivers. The Milky Way galaxy is home to somewhere between 100 and 400 billion stars. That's an almost incomprehensible number, but what's even more remarkable is how slowly everything moves on that scale. Our sun takes about 230 million years to complete one orbit around the galactic center, just one lap. The last time our sun was in this exact position in the galaxy, dinosaurs were beginning their reign on Earth. The Triassic period was just starting. And the next time it returns here, life on Earth, if it still exists, will be unrecognizably different. Galaxies move like slow rivers, vast and patient, taking hundreds of millions of years to make a single turn. And yet, despite their size and slowness, galaxies are not isolated. They exist in clusters, bound together by gravity, slowly dancing around each other. The Milky Way is part of what's called the local group, a collection of more than 50 galaxies, all gravitationally connected. Our nearest large neighbor, Andromeda, is approaching us at about 110 kilometers per second. That sounds fast, but over cosmic distances, it's a gentle drift. In about 4 to 5 billion years, the two galaxies will begin to merge, their stars intermingling like two clouds of fireflies slowly blending into one. The night sky will look different then. Andromeda will grow larger and larger in our sky over millions of years, until eventually the two galaxies begin to interpenetrate. But here's something remarkable. Even when galaxies collide, individual stars almost never hit each other. The distances between stars are so vast that they simply pass by one another, their paths altered by gravity but not by direct impact. It's like two swarms of bees flying through each other. The swarms mix, but the individual bees rarely collide. The merger will take billions of years to complete. Eventually, the Milky Way and Andromeda will settle into a new configuration, probably forming a large elliptical galaxy that some astronomers have nicknamed Milk-O-Meda. By then, our Sun will be nearing the end of its life, and Earth, if it still exists, will be a very different place. For now, everything is as it should be, slow, steady, and unfolding in its own time. The sound of stars. Stars make sound, not the kind we can hear with our ears, of course. Space is a vacuum, and sound needs a medium like air or water to travel through. But stars vibrate. Deep within their cores and across their surfaces, pressure waves ripple and pulse, creating what scientists call stellar oscillations. These vibrations are like the ringing of a bell or the hum of a tuning fork, except they happen on a scale almost too large to comprehend. By studying these oscillations, astronomers can learn about a star's interior, its age, its composition, even its rotation. It's called astroseismology, the study of starquakes. Our own Sun rings with millions of different frequencies at once, each one corresponding to a different mode of vibration. If we could hear it, the Sun would sound like a vast, complex chord, a symphony of overlapping tones, all playing simultaneously. Some frequencies take 5 minutes to complete one cycle. Others resonate over hours. The Sun's surface rises and falls by small amounts as these waves pass through, creating patterns that scientists can detect and measure. Each pattern tells a story about what's happening deep inside the Sun, in regions we can never directly observe. It's like listening to the inside of a drum by analyzing how its surface moves. And it's not just our Sun. Every star in the sky is humming in its own unique way, creating a kind of cosmic music that we're only just beginning to understand. Some stars pulse regularly, like cosmic metronomes. Others vibrate in more complex patterns, with multiple frequencies overlapping and interfering. Red giants, near the end of their lives, have slower, deeper oscillations. White dwarfs ring with higher frequencies, like tiny bells in space. Even black holes, when they collide, send out gravitational waves that could be thought of as a kind of sound in space-time itself, a deep bass note that propagates across the universe. The universe is not silent. It's filled with sound we can't hear, vibrations traveling through gas and plasma and the interiors of distant stars. Even in the quietest moments, the cosmos is singing.
Nebulae, the birthplaces of stars. When you look at images of nebulae,
those colorful clouds of gas and dust scattered through space, you're looking at stellar nurseries. These are the regions where new stars are born, where gravity slowly pulls matter together over millions of years until it becomes dense enough and hot enough to ignite. The process is slow and gentle. A nebula can be hundreds of light years across, and within it, pockets of gas begin to collapse. As they collapse, they heat up. The atoms move faster, collide more often, and generate thermal energy. Eventually, if the conditions are right, the center of the collapsing cloud becomes hot enough for nuclear fusion to begin, and the new star is born. The leftover material often forms planets, moons, asteroids, and comets, creating an entire solar system around the new star. Our own solar system formed this way about 4.6 billion years ago, condensing out of a cloud of gas and dust left behind by earlier generations of stars. The atoms in your body were once part of that cloud, drifting through space, slowly coming together, eventually becoming part of a planet where life could emerge. Nebulae come in many forms. Some are bright and glowing, lit from within by young, hot stars. These emission nebulae shine because ultraviolet light from nearby stars ionizes the gas, causing it to fluoresce in beautiful colors. Hydrogen glows red, oxygen can glow green or blue, and sulfur adds yellows and oranges to the palette. Others are dark, visible only as silhouettes against brighter backgrounds. These dark nebulae are dense clouds of dust that block light from stars behind them. They look like holes in the sky, but they're actually some of the densest regions in space, places where star formation is likely to occur. The Eagle Nebula, the Carina Nebula, the Orion Nebula, each one is a place where the universe is actively creating, where matter is organizing itself into new structures, new possibilities. The famous pillars of creation in the Eagle Nebula are towering columns of gas and dust where new stars are being born right now, hidden inside the dense material. These regions are not chaotic, they're patient. They follow the same physical laws that govern everything else, and they unfold over timescales that make human lifetimes seem like single heartbeats. There's something deeply calming about that. The universe is not in a hurry. It has time. All the time there is.
Cosmic dust and you. Dust is everywhere in space. Not the dust you find under furniture, but tiny particles of carbon, silicon, and metals, each one smaller than a grain of sand. These particles form in the outer layers of dying stars and are blown into space by stellar winds and supernova explosions. Over time, this dust spreads through galaxies, mixing with gas, forming clouds, and eventually becoming part of new stars and planets. The Earth itself is made of this dust. So are you. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen you breathe was once part of a star. Carl Sagan famously said, "We are made of star stuff," and it's literally true. The heavier elements that make up your body, everything except hydrogen and helium, were forged in the cores of stars and scattered into space when those stars died. You are recycled stardust, a temporary arrangement of atoms that have been cycling through the universe for billions of years. Think about that for a moment. The iron in your blood was created in the heart of a massive star that exploded billions of years ago. The calcium in your bones was forged in stellar furnaces. The carbon that forms the backbone of every molecule in your body was manufactured in the cores of dying stars, then expelled into space to eventually become part of a new solar system. And one day, long after you're gone, those atoms will continue their journey. They'll become part of the Earth, then perhaps escape into space, join a new nebula, and eventually become part of a new star, a new planet, maybe even new life. You are not separate from the universe. You are a wave in its ocean, a breath in its wind, a brief and beautiful pattern in an endless flow. This connection is profound. When you look up at the stars, you're not looking at something distant and foreign. You're looking at your origin, your family, your home. The atoms that make you possible came from out there, and they'll return out there eventually. You are the universe experiencing itself, matter that has become conscious, capable of wonder.
The speed of light is really slow. We think of light as fast, and it is by human standards. Light travels at about 300,000 kilometers per second, which means it could circle the Earth 7.5 times in 1 second. Nothing with mass can travel faster than light. It's the universal speed limit, built into the fabric of space-time itself. But on cosmic scales, light is surprisingly slow. The sun is about 150 million kilometers away, which means sunlight takes about 8 minutes and 20 seconds to reach Earth. When you look at the sun, please don't actually look directly at the sun, you're seeing it as it was more than 8 minutes ago. If the sun suddenly vanished, we wouldn't know for over 8 minutes. The light from the nearest star system, Alpha Centauri, takes over 4 years to reach us. That means when you look at Alpha Centauri, you're seeing it as it was 4 years ago. If there were planets there with intelligent life looking back at us, they would see Earth as it was 4 years ago. We could never have a real-time conversation. Any message would take years to arrive. When we look at distant galaxies through telescopes, we're seeing them as they were millions or even billions of years ago. The light we're receiving left those galaxies long before humans existed, traveled through expanding space, and is only now arriving at our eyes. In a very real sense, telescopes are time machines, showing us the ancient past. The most distant objects we've observed are galaxies whose light has been traveling for over 13 billion years. We're seeing them as they were when the universe was young, just a few 100 million years after the Big Bang. Those galaxies don't look like that anymore. They've evolved, merged with other galaxies, changed completely. But their ancient light is still on its way to us, carrying information about the early universe. This means the universe we observe is not the universe as it is now, but as it was at many different times, all mixed together. When you look at the night sky, you're seeing a patchwork of different eras. Some stars as they were decades ago, others as they were thousands of years ago, and distant galaxies as they were billions of years ago, all arranged in a single view. There's something strangely peaceful about this. The universe is so vast that even light, the fastest thing there is, takes its time crossing it. There's no rush, no urgency, just slow, steady travel across the gentle expanse of space.
Planets without suns. Not all planets orbit stars. Some drift through space alone, untethered to any solar system, floating in the darkness between stars. These are called rogue planets, and astronomers believe there might be billions of them in our galaxy alone, possibly even outnumbering stars. How do planets become rogues? Sometimes they form in a solar system but are rejected by gravitational interactions with other planets or passing stars. Imagine a young solar system, chaotic and turbulent, with planets still settling into their orbits. A close encounter between two planets could fling one of them outward, accelerating it to escape velocity. It would leave the system forever, becoming a wanderer in the dark. Other rogue planets might form on their own in interstellar space, like small failed stars that never gathered enough mass to ignite. These objects would form from collapsing gas clouds, just like stars, but they'd be too small to sustain nuclear fusion. They'd be planet-sized from the start, born alone in the dark. These worlds are dark and cold, with no sun to warm them, no days or nights in any meaningful sense. If they have atmospheres, those atmospheres would be frozen or perhaps just barely sustained by internal heat. Some might have liquid water deep underground, heated by the planet's core, creating hidden oceans in complete darkness. Life on a rogue planet would be very different from life on Earth, if it could exist at all. There would be no photosynthesis, no seasons, no sunrises, just endless night, lit only by the faint glow of distant stars and perhaps the auroras caused by cosmic rays striking the atmosphere. Any life would have to rely on chemical energy from the planet's interior, much like the extremophiles we find near hydrothermal vents on Earth's ocean floor. Some rogue planets might be warm enough to support life. If a planet is large enough, it could retain significant heat from its formation, and radioactive decay in its core could provide warmth for billions of years. Combine that with a thick atmosphere to trap the heat, and you might have liquid water on the surface or in subsurface oceans. These lonely worlds remind us that planets are more diverse than we once imagined. Not everything fits neatly into a solar system. Some things wander, some things drift, and that's okay. The universe has room for wanderers. There's a certain poetry in the idea of planets drifting alone through the dark, carrying entire worlds of geography, weather, and perhaps even life through the empty spaces between the stars.
The color of the universe. If you could step outside the universe and look at it from a distance, what color would it be? Astronomers have actually calculated this. By averaging the light from all the galaxies, stars, and nebulae, they determined that the average color of the universe is a shade of beige, sometimes called cosmic latte. This might sound disappointing. Beige isn't exactly the most exciting color, but there's something oddly comforting about it. The universe in its entirety is a warm, neutral tone, not harsh, not extreme, just a soft, gentle color that you might paint on the bedroom wall if you wanted something calming. Of course, this is an average. Up close, the universe is full of vibrant colors. The red glow of hydrogen nebulae, the blue blaze of young hot stars, the orange and red of older, cooler stars, the yellows and greens sometimes seen in auroras and certain types of nebulae, but blend it all together and you get something mild and peaceful. The calculation was done by averaging the light from over 200,000 galaxies, creating a spectrum that represents the entire universe's overall color. When that spectrum is converted to what the human eye would perceive, it comes out as this gentle beige, a color that sits comfortably between white and tan. The universe, it turns out, has a gentle aesthetic. It's not trying to overwhelm you with intensity, it's just being itself, calmly existing in its soft, cosmic beige. There's something reassuring about that. Even on the grandest scale, blending everything together, the universe is subtle and calm.
Moons with oceans. Some of the most exciting places to look for life in our solar system aren't planets, they're moons. Several moons orbiting the gas giants Jupiter and Saturn are believed to have vast oceans of liquid water beneath their icy surfaces. Europa, one of Jupiter's moons, is covered in a thick layer of ice, but beneath that ice, there's likely an ocean of liquid water that could be 100 kilometers deep, containing more water than all of Earth's oceans combined. The moon is kept warm by tidal heating, the constant gravitational squeezing from Jupiter that generates internal friction and heat. Europa's surface is covered in cracks and ridges, suggesting that the ice is constantly shifting and breaking. Some areas show signs of water erupting from below, creating temporary geysers that quickly freeze in the cold vacuum of space. These features suggest that the ocean beneath is active and connected to the surface, which would make it easier for spacecraft to sample the water without having to drill through kilometers of ice. Enceladus, a small moon of Saturn, actually spews water into space from geysers at its south pole. These plumes shoot hundreds of kilometers into space, and spacecraft have flown through them, detecting water vapor, ice crystals, and even organic molecules. This strongly suggests a subsurface ocean, and the presence of organic chemistry makes it even more intriguing. Saturn's largest moon, Titan, is another fascinating world. It has lakes and seas on its surface, but they're not made of water. They're liquid methane and ethane, hydrocarbons that exist as liquids in Titan's cold environment. Beneath the surface, there may also be a water ocean mixed with ammonia, creating a complex, layered structure of different liquids at different depths. Could there be life in these hidden oceans? We don't know, but the conditions might be right. Liquid water, organic chemicals, and energy sources. If life exists there, it would be adapted to complete darkness, living near hydrothermal vents on the ocean floor, much like some life on Earth thrives in the deep sea, far from sunlight. The idea that there might be entire oceans, entire ecosystems hidden beneath the ice of distant moons is both humbling and fascinating. Life might be more common than we think. It might not need a sun, just water, chemistry, and time. The universe might be teeming with life in places we never thought to look.
White dwarfs, the final form of stars like our sun. When our sun dies, about 5 billion years from now, it won't explode in a supernova. It's not massive enough for that. Instead, it will swell into a red giant, consuming the inner planets, possibly including Earth, and then shed its outer layers into space, creating a beautiful planetary nebula. What remains will be the sun's core, compressed into an object about the size of Earth, but containing most of the sun's mass. This is called a white dwarf. It will be incredibly dense, with gravity so strong that a teaspoon of its matter would weigh several tons on Earth. A sugar cube-sized piece of white dwarf material would weigh as much as a car. White dwarfs don't generate new energy. They're not fusing atoms anymore. They simply radiate away the heat they accumulated during their active lives, glowing dimly and slowly cooling over billions of years. Eventually, they'll fade to black dwarfs, cold and dark. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still warm enough to glow. The structure of a white dwarf is fascinating. The atoms are packed so tightly that normal atomic structure breaks down. Electrons are stripped from their nuclei and form what's called electron-degenerate matter, where quantum mechanical effects prevent further compression. This creates a strange state of matter that's more dense than anything on Earth, but still not as extreme as a neutron star. There are billions of white dwarfs in our galaxy, former stars now quietly fading, still glowing with ancient heat. They're stable, peaceful objects, no longer burning, no longer changing much, just patiently cooling in the darkness. Some white dwarfs are made mostly of carbon and oxygen, crystallized under extreme pressure into what could be thought of as cosmic diamonds. Others are helium white dwarfs, created through different evolutionary paths. In a way, white dwarfs represent the peaceful retirement of stars. After billions of years of fusing hydrogen into helium, burning brightly and warming planets, they finally rest. They've done their work. Now they can simply exist, quietly, until the universe grows cold around them. There's something dignified about that, a sense of completion and rest after a long, productive life.
The observable universe has an edge, but the universe doesn't. When we talk about the observable universe, we're talking about the region of space from which light has had time to reach us since the Big Bang. This region is enormous, about 93 billion light-years in diameter, but it's finite. Beyond that, there's more universe, we just can't see it yet. The light from those regions hasn't had time to reach us. But the universe itself might be infinite. We don't know for sure. Current observations suggest that space is either flat or very close to flat, which, according to general relativity, would mean it extends infinitely in all directions. If that's true, then beyond the edge of what we can observe, there are more galaxies, more stars, more planets, stretching on forever. This is a strange and profound thought. If the universe is infinite, then everything that can happen will happen somewhere, an infinite number of times. There would be infinite versions of Earth, infinite versions of you living slightly different lives in distant, unreachable regions of space. Some versions would be almost identical to you, others would be quite different, and somewhere in that infinity, every possible variation exists. But even if the universe is infinite, we can only ever observe a finite part of it. The rest is beyond our horizon, separated from us not by space, but by time and the expansion of the universe. Light from those regions hasn't had time to reach us yet. And because the universe is expanding, and that expansion is accelerating, some parts are moving away so fast that their light will never reach us. The edge of the observable universe is called the cosmic horizon. It's similar to the horizon you see on Earth, where the curvature of the planet prevents you from seeing farther. But the cosmic horizon is created by the expansion of space and the finite age of the universe. It's not a physical barrier, it's simply the limit of what we can see. So we live in a bubble of visibility, a sphere of light and information, surrounded by an unknowable expanse. And that's okay. We have enough to explore within our reach. The observable universe alone contains hundreds of billions of galaxies, each with hundreds of billions of stars. That's more than enough to wonder about. That's more than we could ever fully explore or understand.
Gravity is the weakest force. Of the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is by far the weakest. A small refrigerator magnet can overcome the gravitational pull of the entire Earth when it holds a paperclip against the door. Think about that. A tiny piece of magnetized metal can counteract the gravity of an entire planet. Electromagnetism is vastly stronger than gravity. The strong nuclear force, which holds atomic nuclei together, is stronger still, roughly 100 times stronger than electromagnetism at the subatomic scale. The weak nuclear force, responsible for certain types of radioactive decay, is also stronger than gravity by many orders of magnitude. And yet, on cosmic scales, gravity dominates. Why? Because it's always attractive, it never repels. It acts over infinite distances, growing weaker with distance, but never disappearing entirely. And it adds up. Every bit of mass pulls on every other bit of mass, and over cosmic distances, that adds up to enormous influence. Electromagnetic forces cancel out on large scales because there are equal amounts of positive and negative charge in most regions of space. If an object has too much of one charge, it quickly attracts the opposite charge and becomes neutral. But gravity never cancels. There's no negative mass to balance it out. Everything attracts everything else. Gravity shapes galaxies, holding billions of stars in rotating structures. It bends light, creating gravitational lenses that let us see distant objects we couldn't otherwise observe. It controls the expansion of the universe itself, slowing it down through mutual attraction. And it creates some of the most extreme objects in the cosmos, black holes, where gravity becomes so strong that not even light can escape. There's something gentle about gravity, though. It's not forceful or aggressive. It's patient. It doesn't push or shove. It simply invites. It curves space and says, "This way." And everything follows. Not because they have to, but because it's the natural path through curved spacetime. Objects in free fall are actually taking the straightest possible path through curved spacetime. They're not being pulled. They're just moving naturally through a curved universe. You're feeling gravity right now, pulling you gently toward the center of the Earth, giving you weight, keeping you grounded. It's the gentlest of forces, and yet it holds the entire cosmos together. Without gravity, there would be no stars, no galaxies, no planets, no life. Everything would just drift apart, atoms floating in eternal isolation. Gravity brings things together. It creates structure in an otherwise uniform universe. It makes complexity possible. The moon is drifting away. Every year, the moon moves about 3.8 centimeters farther away from Earth. This happens because of tidal interactions between the Earth and moon. The moon's gravity pulls on Earth's oceans, creating tides, and as the Earth rotates beneath those tidal bulges, friction converts some of Earth's rotational energy into heat and gradually transfers angular momentum to the moon, pushing it into a slightly higher orbit. This process has been happening since the moon formed, about 4.5 billion years ago. Back then, the moon was much closer, perhaps only 22,000 kilometers away, compared to about 384,000 kilometers today. The tides would have been enormous, hundreds of meters high in some places, and days on Earth were much shorter, only about 6 hours long. As the moon drifts away, Earth's rotation slows down, and days get longer. Currently, days are getting longer by about 1.7 milliseconds per century. That might not sound like much, but over geological time, it adds up. 500 million years ago, a day was only about 22 hours long. A billion years ago, it might have been closer to 18 hours. Eventually, billions of years from now, the Earth and Moon will become tidally locked, always showing the same face to each other, just as the Moon already shows only one face to Earth. When that happens, the length of a day on Earth will equal the length of a month, about 47 current days. The Moon will hang motionless in the sky for most locations on Earth, only visible from one hemisphere. But don't worry, this is happening very slowly. The Moon will still be here for a very, very long time, still brightening our nights, still influencing our tides, still keeping Earth's axis stable. That stability is important. The Moon's gravitational influence prevents Earth's axial tilt from varying wildly, which helps keep our climate relatively stable. Without the Moon, Earth's axis could wobble chaotically, causing extreme climate variations that would make life much more difficult. It's just gradually, almost imperceptibly, drifting away. Like everything in the universe, it's in motion, slowly changing, gently evolving. The moon that you see tonight is slightly farther away than the moon your great-grandparents saw, and the moon your descendants will see, if humans survive that long, will be a little more distant still. Change is constant, but it's slow, patient, and peaceful.
The coldest place in the universe. The coldest naturally occurring place we know of is the Boomerang Nebula, a dying star about 5,000 light-years from Earth in the constellation Centaurus. The gas in this nebula has been measured at about 1 Kelvin, which is negative 272 degrees Celsius, just 1 degree above absolute zero. It's colder than the cosmic microwave background radiation, colder than empty space, colder than anywhere else we found in nature. This happens because the dying star at the center is expelling gas very rapidly, at speeds of about 164 kilometers per second, and as that gas expands, it cools dramatically. This is the same principle that makes a compressed gas canister get cold when you release the pressure. The Boomerang Nebula is cooling itself through this rapid expansion, creating the coldest known natural environment in the cosmos. Absolute zero, or 0 Kelvin, or negative 273.15 degrees Celsius, is the theoretical temperature at which all molecular motion stops. It's the lowest possible temperature, the point where atoms have minimum possible energy. Nothing can be colder than absolute zero because temperature is fundamentally a measure of molecular motion, and motion can't be less than zero. On Earth, scientists have created temperatures even colder than the Boomerang Nebula in laboratory conditions, cooling atoms to within a billionth of a degree above absolute zero. At these temperatures, matter behaves in strange quantum ways, forming exotic states like Bose-Einstein condensates, where atoms lose their individual identities and behave as a single quantum entity. But out in space, the Boomerang Nebula holds the natural record, a pocket of extreme cold in the vastness of the cosmos, a place where almost nothing moves, where silence is not just auditory, but molecular.
It's a dying star's final breath, cooled to nearly the lowest temperature physics allows. In time, it will warm slightly as it mingles with the surrounding interstellar medium, but for now, it remains the universe's coldest natural place.
Red dwarfs will outlive everything. Red dwarfs are small, cool stars, much smaller and dimmer than our sun, but they're the most common type of star in the universe, making up about 70% of all stars. What's remarkable about them is how long they live. These stars are the ultimate survivors, the tortoises in a race full of hares. Our sun will last about 10 billion years total, and it's already about halfway through its life. Larger stars burn out even faster, sometimes in just a few million years. The most massive stars might last only a few 100,000 years before going supernova. But red dwarfs, because they're so small and burn their fuel so slowly, can last for trillions of years. Some of them might last 10 trillion years or more. The universe is only 13.8 billion years old, which means that every red dwarf that has ever formed is still burning. Not a single one has reached the end of its life yet, and they won't for a very, very long time. The smallest red dwarfs will still be shining long after all other types of stars have died out. In the far future, when all the larger stars have burned out, when galaxies have merged and star formation has ceased, red dwarfs will still be shining, the last embers of stellar light in a darkening cosmos. They'll burn dimly but steadily, outlasting almost everything else in the universe. Eventually, tens of trillions of years from now, even they will run out of fuel and fade, but they'll be the last ordinary stars to do so. There's something comforting about their patience. They don't burn bright and fast like blue giants. They glow gently for incomprehensible lengths of time, making the most of what they have, lasting longer than almost anything else in the universe. They're the epitome of slow and steady, living proof that longevity comes from moderation, not intensity. Some red dwarfs are so small and dim that they're barely stars at all, just barely massive enough to sustain nuclear fusion. Others are larger and warmer, approaching the mass and temperature of our sun, but all of them share this characteristic longevity. They'll be the universe's nightlights, still burning long after everything else has gone dark.
The Great Silence. We've been listening for signs of extraterrestrial intelligence for decades. The search for extraterrestrial intelligence, or SETI, uses radio telescopes to scan the skies for signals that might indicate the presence of advanced civilizations. They listen for narrow-band radio signals, the kind that nature doesn't produce, or for patterns in the noise that might suggest intelligent origin. So far, we've heard nothing. No alien broadcasts, no messages, no evidence that anyone else is out there trying to communicate. This silence is profound and puzzling. This is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked during a lunch conversation, "Where is everybody?" The universe is so vast, about 13.8 billion years old, with hundreds of billions of galaxies, each containing hundreds of billions of stars. There should be countless opportunities for life to arise. So why haven't we detected any? There are many possible explanations, and they range from the hopeful to the sobering. Maybe intelligent life is extremely rare. Maybe the conditions needed for life to not just arise, but to develop intelligence and technology are so specific that we're one of the very few places where it happened. Maybe civilizations don't last long enough to make contact. Perhaps there's a natural filter, something that tends to destroy civilizations shortly after they develop advanced technology. War, environmental collapse, artificial intelligence, or something else we haven't thought of. Maybe the galaxy is full of ruins, dead civilizations that briefly flourished and then vanished. Maybe they're there, but not broadcasting. Advanced civilizations might use communication methods we don't recognize or haven't discovered yet. They might use laser communications, quantum entanglement, or something else entirely instead of radio waves. Or perhaps they're deliberately staying quiet, knowing that broadcasting your presence across the galaxy might be dangerous.
Maybe space is just too big, and the chances of two civilizations existing at the same time and in communicable proximity are vanishingly small. The universe is vast, beyond comprehension, and civilizations might be so scattered in time and space that they never overlap in a way that allows contact. Or maybe we're the first. Maybe intelligence is so new in the universe that we're among the earliest to develop it. Life took 3.5 billion years to develop intelligence on Earth. Maybe that's fast, or maybe it's slow. We don't know. But it's possible we're among the first technological civilizations in the observable universe. We might be the ones who are supposed to go out and explore, to make first contact, to spread life and consciousness to parts of the universe that don't have it yet. The silence doesn't mean we're alone. It just means we don't know yet. And there's something peaceful about that uncertainty, about existing in a universe full of possibility, where the next discovery could change everything we think we know. The universe might be full of life, or we might be unique. Both possibilities are profound in their own way.
The universe is mostly empty. When you picture the universe, you might imagine it packed with stars and planets and galaxies. But the reality is that the universe is mostly empty space, truly, profoundly empty. The vast majority of the universe is a vacuum, with nothing in it at all. Even within our solar system, the distances are staggering compared to the sizes of objects. If you scaled the sun down to the size of a basketball, Earth would be the size of a peppercorn, about 26 meters away. Mars would be a smaller peppercorn, about 40 meters away. Jupiter would be the size of a small marble, about 140 meters away. Neptune would be an even smaller peppercorn, about 800 meters away, and the nearest star would be another basketball, about 6,000 kilometers away. Most of space contains almost nothing. Just a few atoms of hydrogen per cubic meter, some dust, some radiation. In the densest regions of interstellar space, you might find 1 million atoms per cubic meter. That sounds like a lot until you realize that at sea level on Earth, there are about 25 billion trillion atoms per cubic meter. Space is empty in a way that's hard to comprehend. The distances between stars are so vast that if you picked a random point in the galaxy, the chances of it being close to anything interesting are essentially zero. You'd be far from any star, any planet, any nebula. You'd be surrounded by near-perfect vacuum in all directions, with only the faint light of distant stars to break the darkness. And between galaxies, it's even more empty. Intergalactic space is the loneliest place imaginable, with perhaps 1 atom per cubic meter, surrounded by darkness in all directions for millions of light years. The nearest galaxy would be a faint smudge in the distance, and in many directions, you might not see nothing at all for vast distances. But this emptiness isn't a void. It's not nothing. Space itself is something. A flexible fabric that can bend and stretch and carry waves. And even in the emptiest regions, quantum fields exist, fluctuating gently, creating and destroying virtual particles, humming with potential energy. The vacuum has structure and properties. It's not absence, but a different kind of presence. The emptiness of space is peaceful. It's room to expand, room to exist, room for everything to have its place without crowding. It's breathing room on a cosmic scale. And in that vast emptiness, the occasional star or galaxy or planet becomes all the more precious, small islands of structure in an ocean of space.
We are living in a special time. Right now, in the history of the universe, we exist in what might be called a Goldilocks era for observing the cosmos. We can see the cosmic microwave background, the afterglow of the Big Bang. We can observe distant galaxies as they were billions of years ago. We can study the structure and evolution of the universe. We have access to the full history of the cosmos, from its first moments to the present day. But this won't always be possible. As the universe continues to expand and that expansion accelerates, distant galaxies will move beyond our cosmic horizon, their light red-shifted into invisibility. Eventually, billions of years from now, observers in our galaxy will only be able to see our local group of galaxies. The Milky Way and Andromeda will have merged along with the other small galaxies in our local group, and that merged galaxy will appear to be alone in an empty universe. And the cosmic microwave background will fade as it's red-shifted into longer and longer wavelengths, eventually becoming undetectable. The temperature of the CMB is currently about 2.7 Kelvin, but as the universe expands, it will cool further, eventually dropping below the point where our instruments could detect it against the background noise. Future civilizations, if they exist billions of years from now, won't have the same evidence for the Big Bang that we have. They won't be able to see distant galaxies or measure the cosmic microwave background. They'll have to deduce the history of the universe from more subtle clues, or take it on faith based on ancient records. They might not even know that there are other galaxies beyond their own. So, in a sense, we're lucky. We exist at a time when the universe is observable, when we can see deep into its history and far into its structure. We can watch it evolve. We can trace its origins. We can see evidence of the Big Bang, of cosmic inflation, of dark matter and dark energy. This moment, cosmologically speaking, is special. We live in the age of discovery, when the universe is still revealing its secrets to those who look carefully. In the far future, much of this information will be lost, hidden by the expansion of space. But right now, we can see it all. We can piece together the story of everything. And the fact that we're here to observe it, that the universe has become aware of itself through us, even if just for this brief moment in cosmic time, is extraordinary. Out of hydrogen and helium, gravity and time created stars, which created heavier elements, which created planets, which created life, which created consciousness, which created science, which looks back and sees the process that created it. The universe has achieved self-awareness through us.
Dark energy and the accelerating universe. For most of the 20th century, astronomers thought the universe's expansion was slowing down. Gravity pulls everything together, so it made sense that the expansion would gradually decelerate over time. The question was whether there was enough matter to eventually halt and reverse the expansion, leading to a big crunch, or whether the expansion would continue forever, just slowing down gradually. But in 1998, two teams of astronomers studying distant supernovae made a shocking discovery. The universe's expansion is actually accelerating. Galaxies are moving apart faster and faster, not slower and slower. This was completely unexpected and required a fundamental rethinking of cosmology. To explain this acceleration, physicists propose the existence of dark energy, a mysterious force that acts opposite to gravity, pushing space apart rather than pulling it together. Dark energy is thought to make up about 68% of the universe, more than matter and everything else combined. But we have no idea what it is. It might be a property of space itself, a kind of inherent energy that empty space possesses. Einstein actually predicted something like this in his equations, calling it the cosmological constant, though he later abandoned the idea. Or it might be a dynamic field that changes over time, sometimes called quintessence. Or it might be something else entirely that we haven't thought of yet. Whatever it is, dark energy is winning the cosmic tug-of-war with gravity. The universe is not only expanding, it's expanding faster and faster, and this has profound implications for the future of the cosmos.
In the far future, as dark energy continues to dominate, galaxies will move apart so quickly that eventually each galaxy or galaxy cluster will be alone, unable to see any others. The night sky will go dark. New stars will eventually stop forming as galaxies run out of gas. Existing stars will burn out. The universe will grow cold and empty. But that's trillions of years away. For now, we live in an era when the universe is still vibrant, still full of light and structure and possibility. We can see other galaxies, study them, learn from them. We can watch stars being born and dying. We can observe the universe in all its glory. There's something both humbling and comforting about dark energy. The universe is not static or predictable. It's full of mysteries we don't understand, and yet it continues to exist, to evolve, to create beautiful structures even as it spreads apart. The universe is not afraid of its own expansion. It embraces it, continues to create within it, finds ways to exist meaningfully even as everything moves farther apart.
Neutron stars, the densest objects that aren't black holes. When a massive star explodes in a supernova, sometimes the core that remains is compressed into an incredibly dense object called a neutron star. These objects are typically only about 20 kilometers across, about the size of a city, but they contain more mass than the Sun. The density is almost unimaginable. A teaspoon of neutron star material would weigh about 10 million tons, as much as a mountain. If you could somehow bring a sugar cube-sized piece of neutron star to Earth, it would weigh as much as all of humanity combined. At these densities, atomic structure as we know it breaks down completely. Protons and electrons are forced together, forming neutrons, hence the name. The entire star becomes essentially a giant atomic nucleus made almost entirely of neutrons packed tightly together. It's a state of matter that can't exist anywhere else in the universe, except possibly briefly in particle accelerators. Neutron stars have incredibly strong magnetic fields, billions of times stronger than Earth's. They spin rapidly, sometimes hundreds of times per second, because as the core of the original star collapsed, conservation of angular momentum caused it to spin faster, like an ice skater pulling in their arms. Some neutron stars emit beams of radiation from their magnetic poles, and if those beams sweep past Earth as the star rotates, we detect regular pulses, like a cosmic lighthouse. These are called pulsars, and they're among the most precise natural clocks in the universe. Some pulsars keep time more accurately than atomic clocks. At these densities, atomic structure as we know it breaks down completely. Protons and electrons are forced together, forming neutrons, hence the name. The entire star becomes essentially a giant atomic nucleus, made almost entirely of neutrons packed tightly together. It's a state of matter that can't exist anywhere else in the universe, except possibly briefly in particle accelerators. These objects represent one of the most extreme states of matter in the universe, second only to black holes. They're the leftover cores of massive stars compressed to the very edge of what physics allows before collapse into a black hole. They're remnants of violence, but they exist peacefully, spinning in space, slowly cooling over millions of years.
The cosmic microwave background, echo of the Big Bang. About 380,000 years after the Big Bang, the universe reached a critical moment. Up until then, it had been a hot, dense plasma where light couldn't travel far before being scattered. But as it expanded and cooled, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. This is called recombination. When this happened, light was suddenly free to travel through space unimpeded. The universe became transparent. The photons that were released at that moment have been traveling ever since, stretched by the expansion of space from visible light into microwaves. This is the cosmic microwave background,
or CMB. We can detect this ancient light today as a faint glow coming from all directions in space. It's remarkably uniform, the same temperature everywhere to within a few parts in 100,000. But there are tiny variations, tiny temperature differences that represent the seeds of all future structure. Where the CMB is slightly warmer, there was slightly more matter. Where it's slightly cooler, slightly less. These tiny density variations grew over time due to gravity, eventually becoming the galaxies, galaxy clusters, and the cosmic web we see today. The pattern of variations in the CMB tells us about the composition of the universe, its age, its geometry, and its history. It's one of the most important discoveries in cosmology. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent noise in their radio antenna. They tried everything, even cleaning out pigeon droppings, but the noise remained. Eventually, they realized they were detecting the afterglow of the Big Bang itself. Since then, we've mapped the CMB in increasing detail, using satellites like COBE, WMAP, and Planck. Each new map reveals more about the early universe, refining our understanding of how everything began. The CMB is baby picture of the universe, showing it as it was just 380,000 years after the Big Bang, before any stars or galaxies had formed. Looking at the CMB is like looking back in time to the very edge of the observable universe. It's the oldest light we can see, a direct signal from the early cosmos. And it's everywhere, filling the entire sky with gentle microwave radiation, quietly telling the story of our cosmic origins.
Saturn's rings are temporary. Saturn's magnificent rings are one of the most beautiful sights in the solar system. They span hundreds of thousands of kilometers, but are remarkably thin, in some places only about 10 meters thick. They're made of countless particles of ice and rock, ranging from tiny grains to house-sized boulders, all orbiting Saturn in thin, flat sheets. But these rings won't last forever. In fact, on cosmic timescales, they're temporary. The rings are slowly falling into Saturn, pulled down by the planet's gravity in a process called ring rain. Particles in the rings are constantly being charged by sunlight and Saturn's magnetic field, and these charged particles interact with Saturn's magnetic field in complex ways that cause them to spiral inward. Current estimates suggest that Saturn's rings might be relatively young, perhaps only 100 to 200 million years old. They might have formed from the breakup of a moon that wandered too close to Saturn, or from the remnants of a collision between moons. And they might last only another 100 million years or so before they're completely gone, fallen into the planet, or escaped into space. This means that we live in a special time when Saturn has rings. In the distant past, it might not have had them. In the distant future, they'll be gone. If humans had evolved 100 million years earlier or later, we might never have known Saturn as the ringed planet. We might have seen it as just another gas giant, slightly less spectacular than the others. Jupiter, Uranus, and Neptune also have rings, but they're much fainter and less spectacular than Saturn's. Those rings are also temporary, constantly being replenished by impacts on small moons and gradually falling into the planets. Rings seem to be a transient feature of gas giants, coming and going over geological time. There's something poignant about the temporary nature of Saturn's rings. They're beautiful, but they won't last. They're a reminder that nothing in the universe is permanent, that even the most spectacular features are temporary patterns in the endless dance of matter and energy. Enjoy them while they're here.
The multiverse. Infinite universes beyond our own. Some theories in physics suggest that our universe might not be the only one. There might be a vast multiverse, a collection of many universes, possibly infinite in number, each with its own properties,
laws of physics, and history. One version of the multiverse comes from cosmic inflation theory. If the early universe underwent a period of exponential expansion, as most cosmologists believe, that inflation might not have stopped everywhere at once. In some regions, it might still be going on, creating an eternally inflating multiverse where new universes constantly bubble into existence. Another version comes from quantum mechanics. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. In this view, there are countless parallel universes, one for every possible history. String theory suggests yet another type of multiverse, where different universes might have different numbers of dimensions, different fundamental constants, different particles and forces. The laws of physics might be different in each universe, making some inhospitable to life, while others, like ours, have just the right conditions. We might never be able to prove or disprove the existence of other universes. By definition, they're beyond our observable universe, causally disconnected from us. We can't send signals to them or receive signals from them. They might as well not exist from our perspective. But the idea is philosophically interesting. If there are infinite universes, then everything that can happen does happen somewhere. Somewhere, there's a universe almost identical to ours, except you made a different decision this morning. Somewhere, there's a universe where Earth never formed. Somewhere, there's a universe with completely different physical laws where matter and energy behave in ways we can't imagine. Or maybe, there's just one universe, ours, unique and alone. Maybe the multiverse is just a mathematical possibility that doesn't correspond to physical reality. We don't know. But either way, the question reminds us of how much we don't know about the nature of reality, about the limits of existence, about what lies beyond the edge of everything we can see.
Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape from inside. They form when massive stars collapse at the end of their lives, or when matter accumulates in the centers of galaxies, or possibly in other ways we don't fully understand. The boundary of a black hole is called the event horizon. It's not a physical surface, just a mathematical boundary marking the point of no return. Once something crosses the event horizon, it can never come back. All paths lead inward toward the singularity at the center. From outside, a black hole looks like a perfect sphere of darkness, surrounded by the distorted light of background stars and any matter falling in. If there is an accretion disk of hot gas spiraling into the black hole, it glows brightly, heated by friction to temperatures where it emits X-rays. But the black hole itself is invisible, a dark circle against the sky. Time behaves strangely near black holes. As you approach the event horizon, time slows down relative to someone far away. At the horizon itself, from an outside perspective, time appears to stop completely. If you watch someone fall into a black hole, you'd see them slow down, getting closer and closer to the horizon, but never quite crossing it, their image frozen and fading as light is redshifted away. But from the perspective of someone falling in, nothing special happens at the event horizon. You'd cross it in finite time, not even necessarily noticing the moment you passed through. You just keep falling, faster and faster toward the singularity. The tidal forces would eventually tear you apart in a process called spaghettification. But for a supermassive black hole, you might survive past the event horizon for a little while before the tides became unbearable. At the center of a black hole is the singularity, a point where density becomes infinite and our understanding of physics breaks down. We don't really know what happens there. General relativity predicts the singularity, but we know that general relativity isn't the final word. Quantum mechanics must play a role, but we don't yet have a theory that successfully combines the two. Black holes aren't cosmic vacuum cleaners, despite their reputation. They don't suck things in any more than any other massive object. If the sun suddenly became a black hole, which it can't, it's not massive enough, the planets would continue orbiting exactly as they do now. The only difference would be that sunlight would disappear and the solar system would freeze. But black holes are still extreme objects, pushing the laws of physics to their limits, creating regions where space and time behave in ways that seem almost impossible. They're cosmic laboratories for testing our theories of gravity and space-time, and they continue to surprise us with new discoveries.
The sun's atmosphere is hotter than its surface. This is one of the strangest puzzles in solar physics. The surface of the sun, the part we can see, is about 5,500 degrees Celsius. But the sun's atmosphere, called the corona, is millions of degrees Celsius. This seems to violate everything we know about heat flow. Heat should flow from hot to cold, not the other way around. So how does the corona get so hot? Scientists still aren't entirely sure, but the leading theories involve magnetic fields. The sun's magnetic field is complex and dynamic, constantly shifting and reconnecting. When magnetic field lines reconnect, they can release enormous amounts of energy, heating the surrounding plasma. This process, called magnetic reconnection, might be responsible for the corona's extreme temperatures. Another possibility involves waves traveling up from the sun's interior. Just as sound waves can carry energy through air, magnetic waves can carry energy through the sun's plasma. These waves might dump their energy into the corona, heating it to extreme temperatures. You can see the corona during a total solar eclipse when the moon blocks the bright surface of the sun and reveals the faint glowing atmosphere extending far into space. It's a beautiful sight, with streamers and loops tracing out magnetic field lines. But it's also a mystery, a reminder that even our nearest star still has secrets. The corona extends far beyond the sun itself, gradually thinning out into the solar wind, a stream of charged particles that flows through the entire solar system. This wind carries the sun's magnetic field with it, creating a huge magnetic bubble called the heliosphere that encompasses all the planets. When these charged particles interact with Earth's magnetic field, they create the auroras, beautiful lights in the polar skies.
Galactic cannibalism. Big galaxies eat small ones. Galaxies don't live in isolation. They interact, collide, and sometimes merge. When a large galaxy encounters a smaller one, gravity can tear the smaller galaxy apart, slowly absorbing its stars into the larger structure. This process is called galactic cannibalism, and it's happening right now in our own cosmic neighborhood. The Milky Way is currently cannibalizing several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being pulled apart by the Milky Way's gravity, leaving behind streams of stars that wrap around our galaxy. The Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere, are also being gravitationally stripped, leaving behind the Magellanic Stream, a long trail of gas. This process is how large galaxies grow. The Milky Way has consumed dozens of smaller galaxies over its history, and their stars are now part of our galaxy's halo. In the future, when the Milky Way and Andromeda merge, the result will be an even larger galaxy, enriched by the material from both systems and all their previously absorbed companions. Galactic mergers can look violent in simulations, with stars and gas swirling together in complex patterns. But remember, stars are so far apart that individual stars almost never collide.
The galaxies pass through each other like two swarms of gnats, intermingling but rarely touching. The stars' orbits are changed by the changing gravitational field, creating new structures like tidal tails and stellar streams, but the stars themselves remain intact. Over billions of years, the two galaxies settled into a new configuration, usually a large elliptical galaxy if the merger was roughly equal, or an enlarged spiral if one galaxy was much larger. The central supermassive black holes eventually merge as well, releasing a burst of gravitational waves that ripple across the universe. In the far future, all the galaxies in our local group will likely merge into one giant galaxy, and then that galaxy will be alone, as the expansion of space carries all other galaxies beyond the cosmic horizon. But that's trillions of years away. For now, we live in an era of galactic interaction and evolution, when the universe is still dynamically changing.
The Goldilocks zone. Not too hot, not too cold. For life as we know it to exist on a planet, that planet needs liquid water. And for liquid water to exist, the planet needs to be at the right distance from its star, not too close, where water would boil away, and not too far, where it would freeze solid. This range of distances is called the habitable zone, or sometimes the Goldilocks zone. For our solar system, the habitable zone extends from roughly the orbit of Venus to roughly the orbit of Mars. Earth sits comfortably in the middle of this zone, with liquid water covering most of its surface. Mars is near the outer edge and is too cold for liquid water on its surface today, though it might have had liquid water in the past when its atmosphere was thicker. But the habitable zone is just a rough guide. A planet's atmosphere makes a huge difference. Venus is technically in the habitable zone, but its thick atmosphere traps heat through a runaway greenhouse effect, making its surface hot enough to melt lead. Mars has almost no atmosphere, so even though it receives some sunlight, it can't retain heat. Other factors matter too. A planet's size affects whether it can hold on to an atmosphere. Its magnetic field affects whether that atmosphere is stripped away by stellar wind. The presence of plate tectonics might be necessary for regulating carbon dioxide levels over geological time. The presence of a large moon might stabilize the planet's axis, preventing wild climate swings. And life itself can change a planet's habitability. Earth's atmosphere is 20% oxygen, but that oxygen comes from photosynthetic life. Without life, Earth's atmosphere would be very different, possibly less hospitable. Life can create the conditions for more life, transforming a marginally habitable planet into a thriving biosphere. We've now discovered thousands of exoplanets, and many of them are in their stars' habitable zones. Some are roughly Earth-sized, some orbit in the habitable zones of red dwarfs, where conditions would be very different from Earth, but might still allow for liquid water and life. Each discovery brings us closer to answering the question, are we alone, or is life common in the universe?
Pulsars, cosmic lighthouses. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams, and if Earth happens to be in the path, we detect regular pulses of radiation, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student working with radio astronomer Anthony Hewish. She noticed a strange, regular signal in her data, pulsing with a period of about 1.3 seconds. At first, they jokingly called it LGM-1 for Little Green Men, because the regularity seemed almost artificial. But as more pulsars were discovered, each with its own period, it became clear they were natural phenomena. Today we know of over 2,000 pulsars. Some pulse many times per second. The fastest known pulsar rotates 716 times per second. That's a city-sized object spinning faster than a kitchen blender. Pulsars are incredibly precise clocks. The most stable ones keep time better than atomic clocks on Earth. Some pulsars have been observed for decades, and their pulses arrive with astonishing regularity, accurate to within microseconds. This precision has allowed astronomers to use pulsars for tests of general relativity and for detecting gravitational waves. The Hulse-Taylor pulsar, discovered in 1974, is part of a binary system where two neutron stars orbit each other. By carefully timing its pulses, astronomers could measure how the orbit was changing over time. They found that the orbit was slowly decaying, exactly as general relativity predicted it should due to the emission of gravitational waves. This was the first indirect evidence for gravitational waves decades before they were directly detected. Eventually, pulsars slow down. As they emit energy through radiation and magnetic fields, their rotation gradually decays. Young pulsars might slow down noticeably over years or decades. Old pulsars spin more slowly and pulse less regularly. Eventually, they slow down so much that they're no longer detectable as pulsars, becoming ordinary, slowly rotating neutron stars. But while they last, pulsars are among the most fascinating objects in the universe. Cosmic clocks, laboratories for extreme physics, and lighthouses guiding us through the darkness of space.
Tidal locking, the same face forever. Many moons in our solar system are tidally locked to their planets, meaning they always show the same face to the planet. Our own moon is tidally locked to Earth, which is why we only ever see one side of it from Earth's surface. The far side of the moon was a mystery until spacecraft flew around it and photographed it. Tidal locking happens because of tidal forces. The planet's gravity pulls more strongly on the near side of the moon than the far side, creating a tidal bulge. If the moon is rotating, this bulge tries to rotate too, but the planet's gravity pulls it back, creating friction that slows the moon's rotation. Eventually, the moon's rotation slows down until it matches its orbital period, and the same side always faces the planet. This process takes time. For our moon, it happened relatively quickly because the moon is close to Earth, and Earth is much more massive. But for smaller moons orbiting farther from their planets, it can take longer. Some moons in the outer solar system probably aren't tidally locked yet. Tidal locking can also happen to planets orbiting close to their stars. Many of the exoplanets we've discovered in the habitable zones of red dwarf stars are probably tidally locked, with one side permanently facing the star and the other side in permanent darkness. This creates extreme temperature differences between the day side and night side, which could make such planets inhospitable to life, or could create interesting climate patterns if the atmosphere can circulate heat around the planet. Eventually, over very long timescales, the Earth will become tidally locked to the Moon as well. The same side of Earth will always face the Moon, but this will take tens of billions of years, longer than the Sun will exist, so it won't actually happen before the Sun dies and destroys both Earth and Moon. There's something strangely peaceful about tidal locking. After the chaos of formation, after the unpredictable early solar system, things settle down into stable configurations where the same face always greets its companion, eternal and unchanging across billions of years.
The Voyager spacecraft, messages to the stars. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2, on a mission to explore the outer planets. They flew past Jupiter and Saturn, sending back stunning images and data. Voyager 2 continued to Uranus and Neptune, becoming the only spacecraft to visit those distant worlds. But the Voyager mission didn't end there. After completing their planetary tours, both spacecraft continued outward, heading toward interstellar space. Voyager 1 crossed the heliopause, the boundary where the Sun's influence ends, in 2012. Voyager 2 followed in 2018. They are now in true interstellar space, the first human-made objects to reach that milestone.
Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing sounds and images representing life on Earth. The record includes greetings in 55 languages, music from various cultures, natural sounds like waves and birds, and images showing humans, animals, and Earth itself. The record also includes a diagram showing Earth's location relative to nearby pulsars, using their precise periods as a kind of cosmic address. If an alien civilization ever finds the spacecraft, the record might help them understand where it came from and when it was launched. Of course, the chances of the Voyagers being found are vanishingly small. Space is vast, and the spacecraft are tiny. They'll drift through the galaxy for millions of years without passing close to any star. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. But that's a vast distance. It won't come significantly closer to any star for hundreds of thousands of years. But that's okay. The golden records aren't really for aliens. They're for us. They're a statement that humanity existed, that we reached beyond our world, that we wanted to say hello to the cosmos. They're a time capsule and a message of hope, cast into the eternal darkness, carrying the story of Earth into the future. The Voyagers will outlast everything we've built on Earth. Long after our cities have crumbled, long after all traces of human civilization have eroded away, the Voyagers will still be out there, silently gliding through space, carrying our message to the stars.
Supernovae, the death of stars. When a massive star runs out of fuel, it can no longer generate enough pressure to support itself against gravity. The core collapses in a fraction of a second and then rebounds violently, sending a shock wave through the star that blows it apart. This is a core collapse supernova, one of the most energetic events in the universe. For a brief time, a supernova can outshine an entire galaxy. It releases as much energy in a few weeks as the Sun will emit in its entire 10 billion-year lifetime. The explosion scatters heavy elements into space, seeding the interstellar medium with the raw materials for future stars and planets. There's another type of supernova, called a Type A supernova, which happens when a white dwarf in a binary system accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the mass of our Sun. This is called the Chandrasekhar limit. When the white dwarf reaches this mass, carbon fusion ignites throughout the star almost simultaneously, and the entire white dwarf explodes in a thermonuclear detonation, leaving nothing behind. Type A supernovae are remarkably consistent in their brightness, which makes them useful as standard candles for measuring cosmic distances. Because they all reach the same mass before exploding, they all release roughly the same amount of energy. By observing how bright they appear and comparing that to how bright they actually are, astronomers can calculate how far away they are. This is how astronomers discovered in 1998 that the universe's expansion is accelerating, a discovery that won the Nobel Prize. Supernovae are also responsible for creating many of the heavy elements in the universe. Elements up to iron are created in the cores of massive stars through normal fusion during their lifetimes. But elements heavier than iron require more energy to create than they release, so they can't be made through normal stellar fusion. They require the extreme conditions of a supernova to form. In the intense heat and pressure of a supernova explosion, atomic nuclei are slammed together with such force that they merge into heavier elements. Gold, platinum, uranium, thorium, and most other heavy elements were created in these cataclysmic explosions. Every gold ring, every electronic device containing rare elements, every bit of uranium in Earth's core,
All of it was forged in the death throes of massive stars billions of years ago. Every supernova sends out a shock wave that ripples through space at thousands of kilometers per second. This shock wave can trigger star formation in nearby gas clouds, compressing them and starting the gravitational collapse that leads to new stars. The death of one star can trigger the birth of many others. So supernovae are both endings and beginnings, deaths that enable new births, destruction that creates the possibility for creation. We see supernovae going off in distant galaxies fairly regularly, a few per year visible to our telescopes. Each one is a reminder of the cycle of stellar life and death that has been going on for billions of years. The last supernova visible to the naked eye from Earth was in 1987, in the Large Magellanic Cloud, a small galaxy near the Milky Way, about 168,000 light-years away. Astronomers around the world watched as the light from this stellar explosion arrived at Earth, studying it in detail and learning about the physics of stellar death. Before that, the last nearby naked-eye supernova was observed by Johannes Kepler in 1604. And before that, Tycho Brahe observed one in 1572. These historical supernovae were so bright they were visible during the day and remained visible for months. They challenged the ancient belief that the heavens were unchanging and eternal, proving that even stars could be born and die. Statistically, we're overdue for another supernova in our own galaxy. It's been over 400 years since the last one we could see. When it happens, it will be spectacular, possibly bright enough to cast shadows at night or be visible during the day. Astronomers are watching several candidate stars that might explode soon in cosmic terms. Betelgeuse, the red supergiant in the constellation Orion, has been showing signs of instability and could explode any time in the next 100,000 years. When it does, it will be an incredible sight, a bright new star appearing in a familiar constellation, visible to everyone on Earth.
Rest among the stars. And so we come to the end of our journey through the cosmos. We've traveled from the smallest quantum fluctuations to the largest structures in the universe. We've explored the birth and death of stars, the nature of space and time, the mysteries of dark matter and dark energy. We've contemplated our place in this vast, ancient, beautiful universe. If you're still awake, that's wonderful. I hope these facts have given you a sense of wonder and perspective. If you've drifted off to sleep somewhere along the way, that's perfect too. That's exactly what this video was designed for, to ease your mind, to fill it with gentle wonder, and to help you drift peacefully into dreams. Before we part, let me leave you with one final thought. In all this vastness, in all these billions of galaxies and trillions of stars, in all the incomprehensible stretches of space and time, you are here. You exist. You are conscious. You can think and feel and wonder about all of this. That fact alone is extraordinary. The universe spent 13.8 billion years preparing for your arrival. Stars had to form and die, scattering their elements. Planets had to condense from cosmic dust. Life had to begin, evolve, adapt, and eventually give rise to human consciousness. And here you are, the product of all that cosmic history, lying peacefully, contemplating the very universe that made you. You are not insignificant. You are the opposite of insignificant. You are the universe's way of knowing itself. You are stardust that has learned to think, matter that has become aware, atoms arranged in such a way that they can ponder their own existence. In the entire observable universe, as far as we know, there are very few places where matter has organized itself into consciousness.
You are one of those rare, precious instances. So, as you close your eyes tonight, know that you're connected to everything. The carbon in your cells was forged in dying stars. The oxygen you breathe was created by photosynthetic organisms over billions of years. The water in your body has been cycling through Earth's systems for eons. You are not separate from nature or the cosmos. You are nature. You are the cosmos. You are home.
The universe is vast, but it's not indifferent. It created you. It sustains you. The same laws that govern galaxies also govern your heartbeat. The same forces that bind atoms together bind your molecules together. You are held in existence by the fundamental forces of nature, supported by physics, chemistry, and biology working in perfect harmony. Tonight, as you sleep, the Earth will continue turning beneath you, carrying you smoothly through space at hundreds of kilometers per second. The moon will continue its patient orbit, pulling gently on the oceans, creating tides. The sun will burn steadily, 150 million kilometers away, storing up the light and warmth it will send to you tomorrow morning. And beyond, the cosmos continues its ancient dance. Stars are being born in nebulae right now. Black holes are swirling in the centers of distant galaxies. Neutron stars are spinning hundreds of times per second. Galaxies are slowly colliding and merging. The universe is expanding, creating new space, pushing distant galaxies further and further apart. All of this is happening right now, as you lie here. And it will all still be happening tomorrow and the next day and for billions of years to come. The universe is patient. It's been here for 13.8 billion years, and it will be here for trillions more. There's no rush, there's no urgency, just the slow, steady unfolding of cosmic time. You can rest now. You can let go of the day's worries and tensions. They're small compared to the scale we've been exploring. Not unimportant. Your life matters, your feelings matter, your experiences matter, but small enough to set aside for now. Let them drift away like dust motes in starlight. Let your body relax into gravity's gentle embrace. Feel yourself supported, held securely on this planet's surface. You're not falling, you're resting on a world that has been here for 4.5 billion years and will be here for billions more. You're safe, you're stable, you're exactly where you need to be. Let your breathing slow like the patient rotation of galaxies. In and out, steady and calm. Each breath connects you to the atmosphere, to the trees and oceans that produce oxygen, to the whole web of life on this planet. You're part of something much larger than yourself, and that something is taking care of you, sustaining you, supporting you. Let your thoughts drift like photons traveling through space. They don't need to arrive anywhere particular. They don't need to solve anything. They can just move gently, slowly, without purpose or direction, floating thoughts, soft and distant, like stars in a peaceful sky.
The universe has created this moment for you, this quiet time, this peaceful darkness, this gentle transition into sleep. It's a gift, really. The opportunity to let go, to stop doing, to simply be. In a universe that's mostly empty space, you get to exist. In a cosmos that's mostly cold and dark, you get to be warm and alive. That's something to be grateful for. So thank you for being here. Thank you for taking this journey with me through space and time, through stars and galaxies, through the wonders of the cosmos. Thank you for your curiosity, your openness, your willingness to contemplate the vast and the strange and the beautiful. If you enjoyed this peaceful exploration of the universe, please consider subscribing to the Palette Explainer. There are always more wonders to discover, more mysteries to ponder, more reasons to feel awe and gratitude for this extraordinary universe we inhabit. I create these videos to help you relax, to inspire wonder, and to remind you of the beauty and meaning in existence. You can also like this video if it helped you, or leave a comment sharing your thoughts. Hearing from you helps me understand what resonates, what brings you peace, what you'd like to hear more about. This channel is for you, for anyone who needs a moment of calm in a busy world, anyone who wants to fall asleep to something meaningful and beautiful. For now, though, just rest. Let the universe hold you in its ancient arms. Let the darkness be peaceful, not frightening. Let the vastness be comforting, not overwhelming. You are a part of all of this. You belong here. You are home.
The stars are shining, even though you can't see them through the daylight, or through clouds, or through closed eyelids. They're still there, still burning, still sending their light across the light years. Some of that light is falling on you right now. Photons that have traveled for years or decades or centuries, finally reaching Earth, finally touching you. You are being touched by starlight, ancient light, from distant suns, carrying energy across the void, arriving here, now, at this moment. It's been traveling all this time just to reach you. And tomorrow, more starlight will arrive, and the day after that, and the day after that, forever. You will always be bathed in starlight, always connected to the cosmos, always part of this grand, beautiful, mysterious universe. So sleep well, dear friend. Dream of galaxies and nebulae, of patient red dwarfs and spectacular supernovae, of cosmic webs and dark matter, of space and time bending and flowing like water. Or dream of nothing at all. Either way, you're held safely in the fabric of reality, supported by the laws of physics, embraced by the universe that created you. You are stardust. You are consciousness. You are the universe experiencing itself. And right now, the universe is telling you it's okay to rest. It's okay to let go. It's okay to simply be, without doing, without striving, without worrying. Everything is unfolding exactly as it should. The cosmos is vast and patient and eternal. And you are exactly where you need to be, doing exactly what you need to do, which is simply existing, simply breathing, simply being. Good night, fellow traveler among the stars. May your dreams be vast as space, gentle as moonlight, and peaceful as the quiet darkness between galaxies. Sweet dreams.